We've all been there, in the middle of a job, everything going smoothly, until boom, you're missing a part. United Refrigeration is your one-stop shop for all your refrigeration needs. Use your computer or smartphone to go to www.uri.com at any time of day or night to check stock on your favorite brands, such as Copeland, Sporlan, Carlisle Compressors, Danfoss, Emerson CPC boards and sensors, Carrel, Hussmann Parts, and K2Therm. United Refrigeration Inc. is home to these brands and many more. Looking for information on refrigerant conversions or refrigerant banking? Quick access links on the homepage can get you to the information you need. All approved accounts are able to see live to-the-minute inventory and pricing. Product not in stock at your local branch? No problem. Use the Nearby Stock feature to find a local branch that does have what you need. Are you looking for a branch address, phone number, or after-hours number? That's all available as well. Just click on the branch locator and search for your local branch. Have a model number and looking for a replacement part? www.uri.com/ARP has a vast list of quick pick replacement parts. Just search for the model number of the equipment you're working on and click the Replacement Parts tab. If you don't have an account, click the Register button and we'll have you online in no time. With more than 400 locations in North America, each United Refrigeration branch is fully stocked for immediate pickup. Our branch employees have in-depth technical knowledge, so we can help you get what you need when you need it. Visit your local store or www.uri.com/ARP today. United Refrigeration Inc. has all your solutions down cold.
John, how can you always have the right TV for the right application without carrying hundreds of valves on your truck?
You can carry the hundreds of valves on a trailer behind your truck.
That's too funny. That would work, but how are you going to do that? Maybe there's an easier way.
You can use Sporlan's interchangeable cartridge style Type Q and Type BQ TEVs. Type Q is a conventional design and Type BQ is a balanced port TEV.
Well, come on, I need easy. How easy is it?
Easy as 1, 2, 3.
And it serves thousands of unique applications. So what's the process? How do I put this together?
First, you select the thermostatic element assembly. Then you select the body that you need. Then you select the right size cartridge for the application to get the proper capacity TEV for your application. And then I guess it should also be said you want to actually assemble those into a single valve.
That'd probably be a good idea.
Indeed.
These easy to select and assemble valves mean you're always carrying the right valve for the right job then. If folks want to learn more, what do they do?
You can go to sporlan.com and find more information on the Type Q and BQ thermostatic expansion valves.
I guess that's Jim and John for Sporlan signing off.
Hey guys, here's question number 3 for the month of October. Tell me what Ohm's law is. Let me know your answer at arpgiveaways@gmail.com. Thanks, guys. What's going on, guys? And welcome to Advanced Refrigeration Podcast. You're here with your hosts, Brett Wetzel and Kevin Compass. Where are you at this week, buddy?
Oh, I'm in the wonderful, great state of Ohio.
Yeah?
Yeah.
What are you doing? What are you working on?
Oh, I'm finishing out this controls change out that I started a month and a half ago that the electricians took like a month and a half to pull the wire.
Is that the one that's going from CPC to microthermal?
Mm-hmm.
Oh.
So, yeah, I got to do the HVAC, and of course I did it with zero help until about, I showed up about 2 o'clock today to help me. So
Sweet.
I mounted all the boards, I trimmed all the wires, that all the stuff I had because the other guy had all the parts.
Mm-hmm.
The CTs that microthermal never sent. So that I didn't realize weren't here because they gave me tracking on a box that had one thing in it instead of 30 things.
Yeah.
So, nobody from the shop, bothered to look in it either, when they checked it in. So it was just, your box is here. So, yeah, So another guy showed up finally to help me, and I ran around like a chicken with my head cut off. If anybody's had to service pin microthermal boards before, they know how much of a pain it can be. Well, try doing it by yourself with rooftops. And I don't know who the ignorant asshole who ran this fire pipe inside this rack room was, but it literally, like, there's no way this is code. No way. No way this is like this has to violate OSHA and all this other. Like, literally, you have to squeeze against the ladder in order to get past this 6-inch fire main and the ladder going to the roof.
There's a customer that I deal with in the great state of Texas, and yeah, they have the same situation. And like, towards the end of the day when you're tired, you're not really paying attention, you're gonna rail your head into that pipe because you're not really paying attention on how to get up and down. So I've been there. It's fun. So
thankfully it's been my ass most of the time coming down. So, I've almost just rolled backwards off the ladder. Or it's my tool belt gets caught and like all my shit just goes flying everywhere.
Nice.
But other than that, I mean, it's actually 65 degrees outside, so it's been like sunny, so it's been like actually nice working outside for once.
Yeah, I'm in Cali this week, and it's pretty beautiful out. It hasn't been too hot. It's been fairly just kind of chill. I'm in Cali teaching a level 6 class. Yeah, I told the guys this today. Like, I was like, I'd rather work 24 hours than teach for 8 hours. And it's not that I don't enjoy teaching. It's just like after a day of teaching, my brain is just mush from just being able to, recall stuff that I need to make sure they understand and explaining it a different way. And it's just, I mean, you've trained guys before. It's freaking exhausting. And it's not like the guys aren't getting it. They're doing fucking excellent in class, but it's just, I'm just smoked by the end of the day,
I will trade you in a second. I've been walking across a ribbed metal roof for 2 days straight for 16 hours a day.
That's the only thing I don't like about that particular customer. Every single warehouse is a metal roof, and like there's no, the ribs in there are just at the most. It's just
perfect
not.
Stride. It's like your normal stride. You're fucked. It's like boom, rib. You have to walk in an angle everywhere.
Yeah. You have to work the angle down the fucking roof.
And I'll tell you what, that is the slickest freaking roof there is. Like, I remember last year I was laid up on one for like half hour. I don't even know what happened. I literally, all I remember is walking across and it was like 9 o'clock at night. I just remember walking across and all of a sudden I woke up and I was laying on the ground.
Well, the bitch is that it has the ribs that stick up like 2.5, 3 inches. So when you land, you're definitely going to be fucked up when you get up.
Yeah. Oh yeah. Like it's guaranteed to rack your back.
Yeah.
So guys, today we're going to talk about PID and PID tuning, some like intro stuff. We're not going to go like super, super detailed into it. That'll be another episode. We'll get the interim done first. I mean, there's a lot to go in and go over about this, but like, just so you guys are aware, like with PID tuning and stuff, it should not be.
Hold on. First, we have to explain what PID is, right?
I was going to.
Oh, sorry. Well, like it sounded like you were going to tell a story about how to start tuning.
No,
so.
like I wanted to go over like first of all, like everybody's PID tuning is different, whether it be microthermal, CPC, Danfoss, RDM. Everybody's is different. Some of them are reverse, some of them are forward. Some of them, when you increase values, it makes it slower. Some of them are where you decrease values, it makes them faster. So just for you guys to be aware before we go into all this, like we're going to go over general PID stuff, but everybody's PID is different. So like, don't just take this to heart and, think it's going to be the gospel for every single unit or every single thing. I mean, every single company has their own way of doing PIDs. So, I mean, everyone's going to be a little bit different. I mean, some of them no two are going to be the same. I mean, they all share the same basic principle, but the way that they go about it may be slightly different. Now, with that being said, we're going to go over what is a PID. So a PID is a control sequence, a control loop on how you control something, whether it be a cutting and cut out of a valve, whether it be the analog control of a valve, meaning like you're controlling a say a water valve that's constantly moving. You're controlling to a set point. So you're controlling something to a set point. You have a target set point, and that is what you're trying to maintain.
Let me start off by saying PID stands for proportional integral derivative. The easiest thing to basically understand on what you're really doing here is think of cruise control in your car, right? Your cruise control in your car, you're setting that for a certain speed, right? And that's essentially your P. And then the I is basically how long it's going to take that, like if you set it for 60 miles an hour and you're at 50 miles an hour, basically the amount of time that it's going to take to get from 50 to 60. And the D is basically the amount of change, right? So, if I know that I have to go from 50 to 60, it might step on the accelerator a little bit faster than if I was trying to go from 50 to 55.
Now, with that being said, normally, guys, what we're going to see in HVAC and refrigeration are just PI loops. Hardly do you see PID loops. So full-on PID loops. So the derivative, most of the time, you're not going to see. Most of the stuff we deal with are PI loops, and it is completely fine. I mean, it operates completely fine with just PI loops. When you start getting into PID loops, the D tends to overly complicate things. So a lot of these manufacturers stop it.
That's what my wife says. She says the D complicates things.
I'm not even going to respond to that, but the D and the PID overly complicates things. So a lot of these engineers and people have taken them out of the algorithm. So we just need PI loops. So you see PID loops, like when you start seeing the D loops, it's in like stuff that's like super like fast, critical, like process stuff in like warehouses and like refineries where they need it. We don't need that. We're not dealing with stuff that needs milliseconds, to react. Well, most of the time. Stop it. So
I'm not at my Roadcaster. I do not have my bleep button. Go ahead, continue.
Okay, so we're going to go over proportional first. So proportional is a value which gets added every single time the set point, the control value is away from set point. So it's proportional. So it moves with it. So if, say, your set point is, say, a valve is 20 degrees, it's trying to maintain a 20-degree set point. Okay, and your PI loop is PI is set to 2. Okay, so it's going to multiply by 2 every time it gets above set point. So if it's at 20 and you get to 25, it's going to keep multiplying that value every time the PI loop runs. So it's going to keep multiplying, trying to bring that back down to set point. So the PI loop only is trying to bring things back down to set point. Okay, and then likewise, if it gets below set point, it's going to take away from that value until it gets back to set point. Now, the P is just a proportional. So if it goes up so much away from set point, if there's so much air away from set point, it's going to keep adding. If there's so much air below set point, it's going to keep subtracting until it's back down to 0. Now, the problem with the P is you end up with these mountains inside the control value. The control value is going to be whatever you're controlling: temperature, pressure. It's an analog value. It's that you're trying to maintain. Now you have a set point. So you have a control value and a set point. So the set point is going to be whatever you're trying to maintain. Your control value is however you're getting away from set point. It's your input. Now they're constantly comparing the two. And as you get away from it, it's going to add P to it. As you come back down, it's going to start subtracting P from it. Now, as you change this, so as you start to add more and more P, if you start to speed it up, so say if the higher P value is a faster reaction. So as you start to react faster, it's going to add more, and then it's going to subtract more. It's going to be constantly be, like a mountain. So this is where I comes in. I ends up, smoothing things out over time. So it looks at, okay, so this set point, it's drifting away. So the set point's 20, it's at 25. Okay, well, we added P to it. It's not coming down. Now we're going to add I. I adds over time. So every time the loop runs, it's going to add I. Ends up doing is I ends up taking and smoothing out the mountains. So where you would have these peaks and valleys with the P loop, you're going to have peaks and valleys. You want to try to get the peaks and valleys as low as you can before you start adding I. Once you start introducing I gain into the actual algorithm, then that's going to start bringing you basically to where you're barely overshooting or not overshooting at all, or undershooting. That I value adds to that loop over time. Now, with that being said, the D value, I don't have a lot of experience adding the D's in there because, we don't really use it that much. I generally believe the PID, if I'm doing like tuning, I'll leave the D at 0. And if I'm starting out tuning, the way I do this is I will set the I gain to 0, I will set the D gain to 0, and I will start at like 0.2, and I will start introducing a little bit of P at once. So a little bit of P, I'll get the peaks and valleys to start coming down. Then I'll add a little bit more to where to my graphs start to look way less, like mountains, and they're just slight peaks over. And then I'll start adding I. Now, so with Emerson stuff, guys, a higher value in Emerson is faster. A higher value in Dixel stuff is faster. So meaning if a P value of 1 is a lot. So it'll start, adding up quick. An I value of 1 is a lot. So generally I'll start out with a P value in CPC at 0.20. So I'll start adding more and more and more. The issue is with Emerson stuff is the update rates. You got to watch. A lot of Emerson stuff is 20 seconds, 2 seconds, 4 seconds. The lowest you can go on CPC is 2 seconds. So a lot of other process loops run every second or every half second. Like microthermals, every half second to a second. So that loop updates. So that's one thing you got to take into account is how fast this loop is updating. Because if you're trying to update a PID loop every 20 seconds, it's not going to work. So if you're trying to do a control algorithm and you're trying to maintain and you're updating it every 20 seconds, you're just fighting yourself. Because by the time the input updates, that's 1 to 2 seconds. By the time the control updates, there's another 2 seconds. And then by the time the PID is added to the output, there's 20 seconds. So now 24 seconds have gone by. Now, if you don't have something that's reacting super fast, that's okay. But if you're trying to control a valve that's say a CDS valve doing a defrost differential valve, 24 seconds is going to kill you. You're going to overshoot or undershoot big time. So that's why you need to make sure that PI loop is updating as fast as it possibly can. So,
hey guys, today's episode is sponsored by Westermeyer Industries Serviceable Oil Floats. Many oil separators contain an oil float to effectively meter separated oil back to the compressors. Westermeyer Industries has taken this concept and perfected it with their new line of serviceable oil floats. These floats feature an improved design with fewer components, allowing for greater manufacturer consistency and up to 20% increased oil flow versus their legacy models. These floats also feature an integrated magnet to shield the oil path from debris and have been field proven in supermarket applications. Westermeyer Industries offer replacement oil floats not only for their own separators, but also cross-compatible models for our competitor oil separators as well. You can find out more about the Westermeyer Industries serviceable oil floats by visiting westermeyerind.com westernmeyerind.com/floats. Once again, that's westernmeyerind.com/float. Let's get on with the episode. Hello, guys. This episode is brought to you by Fieldpiece. The tough wireless vacuum gauge MG44 from Fieldpiece is engineered to give you the reliable reading you need and the ease that you want. Confidently measure vacuums with a reliable leak-proof seal. The MG44 can be used with the JobLink system app from up to 1,000 feet away. This easy-to-read backlit LCD offers a graphical representation of the vacuum progress, even in low light or at odd angles. Visit www.fieldpiece.com for information or follow us on social media at Fieldpiece Products. Thanks again and enjoy the episode.
With CPC stuff, you're going to control a valve actuator and you're using like a EPR board. So that EPR board update rate's 15 seconds from the factory. So you need to change it to 2 seconds. So even on CPC, okay, you have a 2-second update rate on the input. You have a 2-second update rate on the EPR board, and now you have the loop sequence control, which is going to be your main driver of the main PID loop, is 15 seconds. So you need to change that to 2 seconds. So even with that, you're still at a 4 to 6 second update rate. I mean, 4 to 6 seconds is pretty laggy. So I mean, you may be fighting that also. That's one thing to keep in mind, guys, when you are tuning these. You want that information coming into whatever you're doing as fast as possible. So you want to be able to have the update rates as low as you can have, so that way everything's updating. Now, when you're going about it, just start low with the P number and just start adding a little bit more till you get it like somewhat stable, and then start adding a little bit of I to it. And then once you get your I to where you feel like it's, kind of, you went too far and it's kind of overshooting again, it's kind of laggy, take a little bit of I out. So generally, I like CVC stuff, like depending on what it is, I'll try to kind of keep my I gain, below 1. And then my P gain, I mean, most of the time it's like 1.1 to 1.5. Like Danfoss stuff is, I haven't really messed with Danfoss stuff besides the CO2 controls. So, I mean, those are, the higher the number, the faster. Microthermal is a toss-up. Like some of the new stuff, the higher the number, the slower. The older stuff, the higher the number, the faster. So it really just depends on, and it depends on what application you're working on. Like some suction group stuff, the higher the number, the slower it is. So it really just depends. You're gonna have to read the manufacturer's spec on whatever it is you're trying to control. For that, I mean, Brett, have you messed with much Danfoss stuff, like for the PID tuning stuff, like on?
No, sir.
So yeah, I haven't really messed with much Danfoss stuff besides the CO2 controls, but like microthermal, same thing. Like we'll start out, like microthermal uses like base values too. So that adds something in there. So it starts out with a base value. So you say you may have a 20% base value. So that maybe where it's starting out, it's PID loop. So you're trying to maintain 20% of that loop. So I mean, that's one more thing to throw in there. They again don't use the D side. They just use the PI loop, and then that percentage. The microthermal stuff and the RDM stuff is way closer to industrial PID loops than CPC. CPC is just like really like canned down, but like you get into microthermals, like their loop stuff and like RDM, like I mean those are true PID loops. I mean, what you could do with some of those, I mean, and setting the base values. I mean, and then go ahead, Brett.
Even as something simple as the Sporlan superheat controller and the Sporlan subcooling controller, right? Those actually have a PID loop in there, and actually, what the instructions in there are rather good, and the reason why we do use, once again, we use the I, because sometimes the proportional will experience an overshoot or an undershoot of the set point. So adding that integral, that I, is basically going to enhance the actual algorithm for that case controller or whatever you're trying to control, to basically control a little bit better. And remember, the integral control senses the actual deviation of the actual evaporator. Like if we're talking about evaporator superheat, from the actual set point. This way you can, have that thing, react the way you need. And so, basically Kevin's saying, start off with a very, very simple deviation of set point, with the P first. Am I correct in saying that?
Yeah. So I always start with the P, and then I'll zero out the I and the D. So that way I could, I can make sure that I'm starting with it to try to trim out the mountain.
Gotcha.
Now, I will say this, guys. A lot of guys go like straight to the PID tuning thing. That is the last thing I'm doing. So I'm going to do everything to try to avoid doing this because PID tuning takes a long time. Now, I mean, I don't even know how many hundreds of hours we have into the CO2 control stuff between me and the guy that I work with every day. Like a lot of it's, him, because he actually has time to sit there and babysit it and watch it. But like there's a ton of other things that'll affect PI loops. So, I mean, making sure that your, process variables are right, meaning your inputs, making sure that like you don't have defrost issues or like you don't have some other issue causing the valves to overshoot or undershoot. So like you need to make sure everything is working 100% correctly before you try to tune this. Because if you try to tune garbage in, you're going to get garbage out.
That also includes, making sure that your ranges are correct, making sure your percentages are correct, the amount of steps that particular valve might have. Because if you're trying to tune, like Kevin so eloquently put it, if you're trying to tune shit, you're going to get shit. So if the thing that you're trying to tune isn't set up from the get, you're fighting an uphill battle. Actually, remember that the guy posted, it was a flash tank. He had a flash tank problem, right? And he was asking about PID loop. And I don't know if I was texting him via Facebook or something, but I was like, hey, why don't you try to check your steps first? And that's essentially what he found. The steps for that valve was set for, I think, 6386, and it should have been 2500. So something as simple as that, finding something like that might take care of all your problems.
I've yet to see a flash tank come out from a factory tuned even remotely. What is the truth? I've yet to see a CO2 flash tank come out remotely even close to what it needs to be. So like we were saying, guys, you need to make sure everything is 100% right before you start, trimming back PIDs, and make sure everything is, functional, and make sure that your input is proper and your update rates are good, and that everything is, set up proper for you to do this before you start introducing all these PID loops. Now, when you are looking at this stuff, you need to look at, trends over time. So you need to be watching this. Like PID tuning could take all day. You could spend 8 hours tuning one loop. I mean, it takes time. I mean, it's like 15, 20 minutes in between adjustments.
You could spend 8 hours adjusting and it'd still be fucking wrong.
Oh yeah, I messed with a defrost differential valve, on using a CDS valve. It took me like 15 hours to get it right before I finally got it to where it was right. And then I went to go apply it to a different store, completely different operation. So, I mean, just because it worked in one place doesn't mean it's going to work in all. I mean, some applications are better for that, but like you just need to sit there and you need to watch it. Like, I mean, you just so physically watch the output, how it's reacting, and then watch the graphs over time to watch it, overlay the graphs and see how it is, and then see if it is overshooting. Now, just remember, guys, you got to keep your eyes on this a lot too, because I mean, Emerson, for example, you could have a 2 to 3 minute graphing period. Well, something could look decent in a 2 to 3 minute graph. That it's taking a snapshot every 2 to 3 minutes. So it could look decent, but in 2 minutes, you could have a lot of movement on a valve. Go ahead, Brett.
That's why a lot of times what you should do is utilize your probes, right? Your probes have an instant graphing function, whether it be field piece, whether it be testo. You're going to basically graph that with the measure quick, and be able to use that graph in order to do your PID adjustment, rather than a controller that could potentially have like a 2 or 3 minute or even a 1 minute graph period, depending on how precise you're trying to get.
Yeah, I mean, a lot of times if I'm tuning a loop, I'll make like with Emerson, I'll make a second log group for like 30 seconds, and I'll just log the process variable, the input, and then I'll just log the variable output or whatever I'm trying to maintain. I'll log that. Now, some things you would want to tune, guys. The condenser application works good, but I mean, as soon as you put a VFD on there, it kind of like wigs out.
Man, dude, that's so I disagree with you in the fact that's an unfair statement, because they don't know what the hell you're attaching it to. You know what I mean?
Yeah, I mean, that's why I'm saying it's why it needs tuned. I mean, it works. It's a workhorse.
It gives you the base program to compile on.
Yeah, I mean, the stock condenser application, like as soon as you throw a drive on there, it does some like wonky shit, and like it just doesn't work right. I mean, it starts cycling fans all weird and like controlling the drive. So like that definitely needs PID tuned. Other than that, I mean, the suction group, you don't really have much control over it. The old school suction group, if you're still using that, I have no idea why. There's no little reason to use the old suction group.
EEV control.
Ooh, so yeah.
Well, listen, let's just go through and just state, because like I said, this is supposed to be an intro, right? So let's just state some of the things that you would potentially tune, right? So one of the things would be, electronic expansion valves, EPR tuning, especially if you're trying to control a pressure. A lot of times, we're typically controlling the EPR based off of temperature, of the average of the cases, which isn't really the best thing in the world. And actually, that never made any sense to me. If anything, I'd want to put a pressure transducer on there and have it try to cycle for that. So if you have a lot of overshooting, that's when you start, adjusting the PID loop. Also making sure the valves that you have aren't oversized for what you have, because that might affect your total PID adjustment as well. Any kind of modulating heat valves, anything where you're basically trying to control an analog value with an analog style valve, something that's going to be, or varying output, right? And that's, Kevin was talking about a loop sequencer. And just to remind you guys, a loop sequencer is basically a control that takes an analog value, takes a set point, and tries to maintain that either with an analog output or a digital output, or it could be a like a bipolar stepper motor or something like that.
So we missed one key thing here.
What's that?
The throttle range.
Yeah.
So, guys, with a PI loop or a PID loop, you have what's called a throttle range. Should have gone over this beginning. I slipped up. So a throttle range is, you see this a lot. You'll see this in the suction group, the condenser control, the suction circuits. You'll see TR, throttle range. So what is throttle range? Throttle range is a set point that it splits the difference usually between above and below the set point, where it starts addressing error. So like meaning, so if you had a 2-degree throttle range, a 20-degree set point, and you were 22 degrees and your set point was 20 and you had a 2-degree throttle range, you are 2 degrees above that set point. So it's going to multiply the P value times the throttle range to find a value that's proportional to that error. So it's going to keep multiplying it by that value. Now, there is a legitimate math equation for all of this. Like if you go online, I'll have to find the links, the things I read to like learn about PID loops. There's a couple control groups where they're really good. Now, don't get me wrong. I understand it to a point. I understand it enough to make it work for me. I do not understand all the math behind it. Like there is a ton of engineer math behind it. Like I'm not going through all that. Like, I mean, there's guys that can sit there and go through all that math. It's a lot. So
Oh no, it's easy. It's 20 to be the evaporator superheat, and the input is X, and let the AE be X by Y, and be the actual superheat, and then so if X is equal, no, yeah, it's
and
complicated.
then some fat cow holds the door open for 20 minutes and looking for ice cream when the glass is see through, and the whole algorithm's out the window. Am I not right? Like I watch it today for like 10 minutes. Like this lady just had the glass door open. I'm like, can you just look through the glass? Like I want to slam your head in the glass. Like shut the door.
You can tell you're in Ohio. You're being very angry.
Well, I mean, it's just like, is that not the most irritating thing ever? You're working on something and they're just like sitting there with the door open, and this is like,
I'm at the point where, like, when I go food shopping, because usually I'll go food shopping at night, so no one's there. So then I don't have the annoyance of just being like, just close the door, just close the door, just close the door. Actually, my local town, it sounds like it's gonna go boom. Like every time I go shopping there, like the motor room, I can hear it all the way downstairs. It's very loud. Something's going on.
I lost my train of thought now. So as the
Fat cow.
no, thanks. Yeah, you know, like you're so good at like making people lose their train of thought. Okay, guys. So all right, the throttle range. So that throttle range is going to deviate whatever, or it's going to make whatever the value is going to get multiplied by. So like the bigger the throttle range, the less reactive it is a set point. That was me. The less reactive it is a set point. The smaller the throttle range, the more reactive it's going to be. So if you have a throttle range at 25, it's going to be a slower reacting throttle range at 2. So if you are PID tuning, I start with the throttle range every time. So adjust your throttle range. I mean, if you have a 25-degree throttle range, you're going to have a slow reacting valve. I mean, if you have a small throttle range, it's going to react really fast to changes in set point.
That would be essentially the deadband, correct? Or are you talking about? Because some controllers it is labeled as TR, but some of them is labeled as deadband. No,
some of it is deadband, some is TR, some of it is base value.
Yeah, so like if you're at a standard suction group that has a deadband, if you're tuning an XM 678 or 679, that's where it has the TR in there.
So the TR in the XM cases is actually the P loop.
Is it really?
Yes. So the TR is the actual P loop in the Dixels.
Mm.
So a higher TR reacts slower in a Dixel for the most part.
It would be really good if you hooked up to a XM 678 or a 679 and basically did like this is what you're going to adjust when this happens, and this is what you're going to adjust when this happens. It'd be a good video to watch.
Yeah. I mean,
haven't made a video in a while. It'd be good. Super
freaking long to react over time. That's the only thing. So like the Dixel stuff, like Brett was talking about, you have a TR or HR. Is it TR or HR in there? I think it's
TR.
HR.
Really? That was TR.
It's either TR or HR, the Italian, whatever they made it over to. But so you have that, and then you also have an integral time in there. So the integral time in the Dixels is like super high. Like off the beginning, it's like 225. So it has a super long integral time. So it adds a ton of error to the set point. Or a ton of I to the set to the error to try to bring it down. We end up bringing those down a lot, and it ends up making it run a lot smoother. But that's just like another thing, guys. Like, yeah, certain things like PIDs out the box are no good. I mean, manufacturers try to get it close, but it's not, a one size fits all. Just because a PID works at this store doesn't mean it's going to work at the next store. I mean, you can get a general like place to start, if you know these, and then as you build up, like I have like a list of, things we like, settings we use at certain places, and they work out pretty well. But I mean, there's times where it falls flat in its face and we got to, start over.
And also, it might differ on like the time of year too, right?
Yeah, I mean, exactly. I mean, it's in the summertime, valves are going to be bigger.
Yeah. So one prime example of this, we have a Cascade rack in one of our stores in Texas, and I adjusted the crap out of the PID loop for the electronic expansion valves, and when it got cold, everything fell on its face. So literally, I had to be there for about 4 hours to get a pseudo good adjustment on the superheat controller to get it to react a lot faster than what it was. And I had to do it when it was cold, because basically it worked fine when it was warm outside, but as soon as it got cold out, my programming went out the window. It was garbage. So when you have those drastic changes in temperatures, it is going to affect the way that the thing's going to react.
Yeah, that is one thing I like about microthermal is like their new condenser application, like it has a summer and a winter set point. Same thing with their CO2 controls for like the gas cooler and the flash tank. They have summer and winter PIDs. So you could change your PIDs for summer and winter. It allows you to like dial it in like so much tighter. Unlike with it, like Emerson and Danfoss, you're kind of just stuck with what it is, and you have to manually adjust it. Like they've already gone and thought about this. Like they can tune it for, you have a summer set point, you have a winter set point, because I mean, in the summertime, you're going to have a way bigger load in your flash tank than the winter. So you're going to have way more hunting in the winter. So when you get to CO2 stuff, when you guys start to see more CO2 stuff, it is nothing but PI loops and PID tuning. And I mean, you got to remember every single valve in a store is electronic. I mean, unless they're, pulse valves. With pulse valves, I mean, you could throw the best tune in the world in there, but it is what it is. It's a solenoid pulsing liquid. So, I mean, it's going to be choppy no matter what. You can make it look okay, somewhat okay, but like you're going to have peaks and valleys and mountains. A pulse valve will never be what a stepper is. I don't care who says what. Like, it's never going to control as good as a stepper.
For sure.
I mean, trimming out pulse valves. I mean, I get them close to where they're not overshooting superheat, and I'm not having case temp issues. But I mean, don't waste all the time in the world trying to tune out pulse valves. I mean, it's just a losing battle. But like steppers, like Brett said, make sure everything is correct first with the stepper. Make sure that it's the right steps and it's zeroed out, because if you're trying to control it like that, I mean, there's going to be definite issues. And then trying to find out like your base values. And then also, if you're tuning like cases and stuff, make sure there's food in there. Don't tune it when there's no food in there, because what's going to happen is it's going to change the entire load, in the case. So, it could be more or less. It's going to, I've made that mistake before. I tuned an entire store, came up with a good tune, spent 8 hours on it, 8+ hours, and it loaded it up. Next day I'm there because a bunch of cases are running warm because they can't keep up.
Absolutely.
All right, guys, that'll be it for tonight on this, and have a nice one.
All right, later, guys.